So last time we were looking at this spectral analysis of graph. So you would feed in either the adjacency list or the adjacency matrix to the jar executable file I gave you, and it would give you the eigenvalues and the eigenvectors. So for each eigenvalue there will be a corresponding eigenvector. And since we are working with the adjacency matrix of a graph, so as I said last time, even if you feed in the adjacency list, internally it will be converted to an adjacency matrix, and that is what is used as input to the spectral analysis program. So for a matrix with all positive entries, mean 0 or more greater than 0, in the case of adjacency matrix we are going to have zeros and ones. The largest eigenvalue, which is called the principal eigenvalue, is guaranteed to be positive, and all entries in that corresponding eigenvector, which is called the principal eigenvector, are also going to be positive. So for example, for this graph, the largest eigenvalue is 3.3893, and this is the corresponding principal eigenvector. And so all entries are positive in this, and also, as I said, each entry corresponds to the corresponding node ID. So this value is a kind of measure of, again, this is called eigenvector centrality of the vertices. So the entries in the principal eigenvector are called the eigenvector centrality. We'll see more about this in the third module, but that is one of the uses of this spectral analysis. So the eigenvector centrality quantifies or is a measure of the degree of the node as well as the degree of its neighbors. So a node that has a larger degree and whose neighbors also have a larger degree is expected to have a larger eigenvector centrality. So in this case, node 1 has a larger degree of 4, and its neighbors 5 has a degree of 5, 2 has a degree of 4, 4 has a degree of 3, 3 has a degree of 4. So all its neighbors basically have a reasonably larger degree. So it's expected to have a larger eigenvector centrality, and that's what you see. Node 1 has the largest among all the vertices. Then you can see just having a larger degree is not sufficient for a vertex to have a larger eigenvector centrality. So node 5, even though it has the largest degree of all the vertices, no other vertex has a degree of 5, but the neighbors of vertex 5 have a relatively lower degree, like 9 and 10 has a degree of 1, 6 has a degree of 2, 7 has a degree of 2, it is 1 that has a larger degree of 4. So the eigenvector centrality of 5 is not that as high as that of vertex 1. And nodes that cannot be distinguished based on the degree as well as the degree of their neighbors. So in this case of 9 and 10, both have a degree of 1, and they have a common neighbor 5. So there's no way we can distinguish 9 and 10. So they have the same eigenvector centrality. So these are some of the things you should be able to interpret from the eigenvector principal eigenvector entries. And also, as I said last time, the eigenvectors are kind of orthogonal to each other. So that means if you take the dot product of two eigenvectors, it's going to be 0. So it means the eigenvectors other than the principal eigenvectors are expected to have some negative entries. So that's why when you take the dot product, the sum will add up to 0. Okay. So any questions on eigenvector spectral analysis? I hope everyone got a chance to try the jar program and run it. So make sure you are able to get it running, and so because you'll be using this to do some of the assignments and exams in this course. Okay. Alright, so let us do the next topic. So some of the applications of the eigenvector approach. So one thing you can do is try to quantify. So as I said in the beginning of this course, one thing that you would try to do is quantify things, so that using those numbers we can interpret some of the characteristics of the networks that we are going to analyze. So one thing we could do with this spectral analysis is to quantify the variation in node degree. So do all the vertices have the same node degree, or they have different degrees? Now you might have come across in a statistics course something called standard deviation or variance that could be used to capture variations in a particular metric that you're measuring. But the standard deviation, the magnitude of standard deviation will be dependent on the actual node degree values. Okay, so for example, if we take up this graph, it has say 10 vertices, and the maximum degree you can get in this graph is 5, and the lowest is 1. So the range of the degree values is 1 to 5. So if you measure the standard deviation, we'll see in detail later, if you have not seen already in a statistics course, the procedure to calculate standard deviation. But it would be between the minimum and maximum, say somewhere around 1, or lower the standard deviation, less the variation in node degree. But it won't go beyond say 5 or something like that, because that's the maximum degree, so it won't be a very large number. On the other hand, consider say a very large graph, and the degree values of the vertices range say from 10 to 100. Then the standard deviation of node degree will also be somewhere of that magnitude, say about 10, 20, around like that. Okay, so you have one graph with 10 vertices that has for which the standard deviation in node degree is around 2, and another graph with 100 vertices or 1000 vertices in which the standard deviation of node degree is like 20, like that. So if I give you the standard deviation values, it's only for the two graphs, you probably would come and say that the second graph with a standard deviation of 20 has a very large deviation in node degrees. But it need not be the case, because the degree values itself in that graph are in the higher range. So the standard deviation would also have some magnitude that corresponds to the range of degree values. Whereas here it's not very high, it's 1 to 5, but the standard deviation is like 2 or 3, it's reasonably larger for this magnitude of node degrees, for the range of node degrees. So what we want to do is, with the spectral radius ratio, with this eigenspectral analysis approach, we want to come up with a measure of variation in node degree that is independent of the number of nodes, that is independent of the actual degree values of the vertices. So we want a kind of a uniform scale. So a graph of 10 vertices and a graph of 1000 vertices should be still comparable to each other on this metric of the capturing the variation in node degree. So that's what we're going to see now. And we'll make use of a very simple relationship that was existing in the literature. So this is a relationship. For any graph, the minimum node degree is observed to be less than or equal to the average degree of the vertices, which is less than or equal to the principal eigenvalue of the adjacency matrix. So for example, in this graph it is 3.3893, that's the principal eigenvalue, and which is less than or equal to the maximum node degree. So this is a very interesting and important relationship that people proved in the literature for any graph. Now we can also call this principal eigenvalue as a spectral radius. So there's a different name for principal eigenvalue, it's called the spectral radius of the graph. So using this relationship, what we could do is, if you take the ratio of the principal eigenvalue and the average degree, okay, so that ratio, because the average degree is less than or equal to the principal eigenvalue, or looking at the other way, principal eigenvalue is greater than or equal to the average degree, the ratio of the principal eigenvalue and the average degree is going to be always greater than or equal to 1. Okay, so for example, if average degree is 2.5 and the principal eigenvalue is like 3.3893, 3.3893 divided by 2.5 is going to be greater than 1. Okay, so the worst case will be equal to, so greater than or equal to 1. So this ratio, the spectral radius ratio for node degree, does not depend on the number of nodes in the graph, and does not depend on the magnitude of the node degrees, because you are taking the ratio of the principal eigenvalue and the average of the node degrees. the magnitude doesn't come into play here, as well as the number of nodes. So using this simple observation and calculating this ratio of node degree, we are able to find or able to capture the variation in node degree. So if all the nodes had the same degree in a graph, if all the nodes had the same degree, then K min will be equal to K average, which will be equal to principal eigenvalue, which will be equal to K max. So in that case, the spectral radius ratio will be just 1. So 1 is the smallest value you can expect for this ratio, and if the ratio for node degree is 1, that means there's no variation in node degree. On the other hand, if there's a lot of variation in node degree, then K min is going to be definitely less than K max, and K average is going to be less than K max or as well as the principal eigenvalue, and the principal eigenvalue will tend to be more larger compared to K average. So more the variation in node degree, the larger this ratio, and that's what we have observed for the real world networks. Okay, so this was published by me in a paper which is cited here, and this paper talks about this measure and a lot of and analyze this ratio for several real world networks. Okay, so let us do some example calculations, and that will be even more clear now. So let us use the same graph we had before, and you want to calculate the spectral radius ratio for node degree. So using this spectral analysis program, you can find the principal eigenvalue, which is the largest eigenvalue among all the eigenvalues that get printed, and this is 3.3893. And then you need to calculate the average node degree. So we saw 3 ways earlier to calculate the average node degree. The simplest way is to just sum up all the node degrees and divide by the number of vertices. That's what I'm showing here. So this is the sum of all the node degrees divided by the number of vertices 10, and that is 2.8. So then to get the spectral radius ratio for node degree, divide the principal eigenvalue by the average node degree, and we get 1.21. So as I said, this is a ratio expected to be greater than or equal to 1, and this is kind of reasonably closer to 1. Now let us do some changes to this graph. So let us delete this edge 1, 5 and add a few edges like 6, 10 and 7, 9 as well as 1, 8 to this graph, and that's this new graph. And because of this link changes, the node degrees would have changed, so you have to recalculate the average node degree, and let us say it comes to 3.2. And if you rerun the principal eigenvalue based on this adjacency list, so again let me show you how we do this calculations. So type the adjacency list, again the format or the what do you call, the rule we follow to enter the adjacency list is start with the lower ID, and the other end vertex will always have the larger ID. So 1, 2, 1, 3, 1, 4 and 1, 8, these are the neighbors of 1. And then move on to node 2. So node 2, you have already covered the lower ID neighbor 1, so just write the higher ID neighbors. So 2, 3, 2, 4 and 2, 6. Then 3, 4, 3, 8. Then for 4, all its neighbors are lower ID, so it would have been captured somewhere earlier. 4, 1, 4, 2 and 4, 3. For node 5, it is 5, 6, 5, 7, 5, 9 and 5, 10. And for 6, it is 6, 10, and 6, 5 is already captured, 6, 2 is already captured, and for 7 it is 7, 8 and 7, 9. For 8 everything is captured already, 8, 7, 8, 1, 8, 3. For 9, 9, 5, 9, 7, 10, 10, 5, 10, 6, all neighbors, all our ID neighbors. So this is the adjacency list, and you can always cross check whether all the edges are written here. Then what you do is you copy this to a text file, or you could have already entered this in a text file. So make sure the last line doesn't have any blank space. So this is the last line where we have the last edge information. So save this to a text file and name the graph. So you could save it anywhere you want. So let us run I'm using the adjacency list based program. So start the execute or double click on executable jar file and load that text file wherever you saved it. Okay, I saved it as graph 2. Okay, so these are my principal eigenvalues, and you have the eigenvectors for each of those eigenvalues. So the largest eigenvalue is 3.473, and this is corresponding principal eigenvector. So here we just need the principal eigenvalue, which is 3.473, and that's what I have written here, 3.4735. So you divide that by the average degree corresponding to this new graph, and you'll get 1.09 as the ratio. So you could see here, even though the average node degree increased from 2.8 to 3.2, it doesn't mean that the variation in node degree should also increase. Okay, so you find that, so given these two graphs, based on the spectral radius ratio for node degree, the 1.21 and 1.09, we can say the second graph has relatively less variation in node degree compared to the first graph. Okay. So that's what you could interpret from these numbers. The larger the variation, variation in node degree, you expect the spectral radius ratio for node degree to be also larger. So the more closer it is to 1, the lower the variation in node degree. So this graph, the second graph after this link changes, is considered to have a lower variation in node degree compared to the first graph. So that's one application of using this spectral analysis approach. Any question?